So we are starting a new venture tonight, and we're going to be comparing population means. So I want to just take a second and orient ourselves as to what we're actually going to be doing with this. If we look back, I'm looking back at the syllabus right now, and I'm looking at all the things we've covered thus far, and everything that we have done has been for a single sample, right? That's what we've been doing so far. Everything we're doing is for a single sample, and then we've been analyzing a single sample. Tonight, we're jumping into a new type of mindset, and that mindset is when we look at two different populations, we're comparing two different things. So we have two populations. We pull a sample from this one, a sample from this one, and then we compare them. Such like that. So where we have began. So the important thing to remember about this is that we are taking two things and comparing them. And so our formulas that we're using, our tests that we're running, are going to be pulling off of two parameters, essentially. It's the same parameter of interest, whether it be means or variances or whatever, but we're comparing two of them. We have two of them, and we have to plug two things essentially into the same spot in a formula now. And so that we're going to learn a way to do that, a couple of ways that we can do that tonight. So let's just take a few minutes and review what we have done that has, all of it comes together to set us up for tonight, okay? We have learned about the empirical rule and the normal distribution, and that our sampling distributions, with the central limit theorem, our sampling distributions point towards the mean of the means is the true mu of the population. So all of that comes from the normality of a data set, and it comes from the central limit theorem and the underlying algebra that allows that to happen. After we learned about that, we started learning about inferences and the way that we can take a sample from a population of interest and then generalize that using inferential statistics, generalizing that sample to tell us about the entire population. And that's a pretty powerful thing because it allows us to utilize statistics in real world scenarios that are, most of which are really out of our practical control. Pretty much any statistical question that you're interested in life is going to involve a population that's larger than you have direct access to. And so the power of inferential statistics is that we can take a sample that is attainable, and then we can use that sample to tell us something about the entire population. It's a powerful thing to think about. And so we learned about that after we learned about sampling distributions and the central limit theorem. The way that all that works is by the central limit theorem and the law of large numbers, okay? And we threw some calculus in there for the MGF cases. But there's theory and there's mathematics, which we're not really going to go into in this class because it's not in the scope of the class, that essentially is the mathematical foundation that allows us to do all of these things. So these are strong relationships that we have, that we know between these things, and those strong relationships have been well tested and well established, and they're backed up by well-established mathematical principles. And so that is what allows us to have all of these tools at our disposal that we're learning about in this class, and know that they work and that they're reliable and that they're real and that they're not just some it's up to some person to come up with a theory that then that's kind of like used. Some of these theories, some of these tests and these laws are named after the person that essentially published them or originally designed it. But in order for it to be taken seriously, of course, it has to be built on some mathematical foundation that is not dependent on one person's creation, right? It has to be built on previously established mathematics. And so even with all of the things that we have learned and the things we're going to learn, that is the case. We are going to change the syllabus just a little bit next week. Our intention is to reincorporate some of what are called non-parametric tests. We edited those out of the curriculum this semester in favor of doing the calculus for the MGFs. So in the previous iteration of the class, we didn't have the MGFs, but we had non-parametrics. This semester, we cut out the non-parametrics in order to do the MGFs. And now we're finding that a lot of the research projects that you guys are doing are going to require non-parametric tests. And so we have a flex day in the calendar. And so we're going to use that and go back and teach some of the non-parametrics and bump the linear regression stuff, I think, to the end. Dr. Misteli is still deciding on how she wants to do that, but that's what we had discussed at our last conversation. So, yep.
Does that mean that she's going to change the due date of our analysis part 3 since we've got to learn Anova testing next week, and that's what we have to do?
She hasn't said anything about that to me yet, but I can certainly ask her. So that was due date for analysis part 3?
Yeah, our analysis project part 3 requires Anova testing, which is listed as what we're going to learn next week. And
Okay.
then the project's due the week after that.
Okay, I'll ask her about that. Okay. Okay, so that's essentially where we are at this point. And everything has been based on a single sample. We're drawing one time, and then we're performing statistics on that one draw. So starting tonight, we're going to be changing that into two draws and comparing them. So let's just do this as a warm-up example. A battery company claims the average lifespan for its batteries is 54 months with a standard deviation of 6 months. Consumer Reports tested this claim using 50 batteries and they found a mean of 52 months. So I want you to take about 4 to 5 minutes and tell me, what do they conclude, okay? Okay, who'd like to share their solution? And feel free to share your screen if you'd like to also. Anyone, any ideas? Okay, I'm going to give you an extra 3 minutes to finish calculating, and then I'd like a volunteer to share their solution. Amanda has gotten failed to reject, so she is accepting the battery company's claim. I want to hear other people who agree or disagree with Amanda. Okay, both Amandas are in agreement.
I agree with the Amandas.
Okay. That was, who said that?
Candace McLaughlin.
Candace, great. Candace agrees. Wes agrees. Are we going to fail to reject here? Amanda wants somebody to disagree with her for a spirited conversation. Looks like we're getting a lot of agreement. Raise your hand or put a green check by your name if you agree with Amanda. And she is saying, fail to reject the null. You are accepting the battery company's claim. John.
Okay, I want to know what people got for their p-value because I think I've made a mistake.
Good question. Always look at the p-value. What p have we gotten here, folks?
I had P was 0.0183, but I could have done something wrong because I was kind of rushing.
I got 0.0184, so...
Which is essentially the same thing. Both of
right?
them are smaller than...
Yeah, well, that's what my calculator says. And I have an Inspire, Jen. I have an Inspire.
Okay.
She told me she wouldn't help me anymore if I didn't get an Inspire.
Oh, okay. All right. Well, I hope that they all give us the same output.
Well, assuming we're putting in the right stuff, is that, garbage in, garbage out.
Okay, so Wes originally said he agrees with fail to reject, but now he's going back on his answer.
Yeah, because if P isn't okay, if P is 0.018, that's less than 0.05.
Yeah.
Correct.
It's even less than 0.025 if we were supposed to cut it in half. So we would reject, right?
Well, if that's the real p-value people are getting.
Yeah.
Mm-hmm.
I had set my problem up as, for my Z statistic, as 52 minus 54 over 6 over square root of 50.
Okay, and I just put it in the Z-test in the calculator. Maybe that's why we have a slightly different p-value.
Yeah, because I found my Z statistic was negative 2.36, and then I put that in, and then I doubled it.
So your Z statistic is going to be negative here because the mean of the sample is 52, which is lower than the mu given by the company. So that's going to give you a negative Z value.
Yeah, because I did it in the Z-test in Inspire, put in X bar is 52, N is 50, and sigma is 6. That Z was negative 2.357, and p-value is 0.018. And that p-value is so low, we should reject the null hypothesis.
Yeah, and I did it two-tailed.
Yeah, that's what I did also. Because it doesn't say they're claiming that they're just saying it's not right. They're not saying it's too big or too low.
Right. Yeah, this would be two-tailed. That you're testing it whether it's 54 or not.
Do we not need to use the table on page 315? Is our N not large enough for this?
Are you using the calculator?
No, yeah, I was using the calculator, but there's a chart on 2 or 315 that's like the rejection regions. Is that not, or do we just base it? based on the p-value being less than alpha to reject the null.
315. Let me look at what 315 is.
Is that the 1.96?
Oh,
Yeah,
yeah.
that
Those
thing.
are just, those are common values. Yeah. Yeah. Right. So, yeah. So that, I mean, that's the same thing we were, that whoever it was said it was negative 2.3. Ron suggested that the z value is negative 2 point something. Yeah, I mean, that's just confirming what's in this table here.
So is that right? Were we right? Still don't know.
You know, I gave a professional development talk a couple years ago, and the title of it was, Did I Get the Right Answer? So I'm going to, if the P is low, reject the ho. That's right. So, okay. So we're going to go into, gosh, I'm having a brain freeze right here. Okay. I'm doing this on an 89. You can do it on an 84 or an Inspire or whatever else you have. So we're going to go to tests. This is a hypothesis test. This is going to be a z-test because it is higher than 30. So it's large enough to use z. We're not doing any two samples or proportions or anything else. So it's just a regular old z-test. I'm going to input the stats. My mu naught is 54. My sigma is 6. My x bar is 52. And n is 50. And the alternative hypothesis is that it is not equal to that. Because we're not, you know, notice the question doesn't say anything like, we are suspicious that it is lower than 54. We're not saying anything like that. We're just testing whether or not 54 is the right number or not. We're not incorporating any predisposed bias as to which direction it's going. So it's just going to be not equal to. And if, I don't know if you can see this, I know it's really small on the 89. So this is my setup right here. Okay.
Alex, did you say that? Okay. I thought I heard you say a 56.
No.
No.
Well, if I did, I spoke the wrong thing, but typed in the right thing.
Okay.
Mu naught is 54. Sigma is 6. X bar is 52. And the n is 50. And then we've got the mu not equal to mu naught. Okay. So that's what we're looking at there. So p-value is 0.018. Gosh, I'm getting past my focal length on this thing. 0.018. So what does that say? This is what I'm getting out of it. Right there. What does that tell us? Reject. Right. That p-value is lower than 0.05, so we reject. Or 0.025, excuse me. It's lower than 0.025 because it's a two-tailed test.
So what is the proper way to say that?
That's a good question. The proper way to say that is we observe a p-value of 0.018, which is lower than either tail of the, which is well actually you can just say we observe a p-value of 0.018, thus there is sufficient evidence at the 0.05 level that the true mean of the lifespan of the batteries is not 54 months. And anybody who was reading that, who knows statistics will know to interpret it that it's a two-tailed test, because you're just saying that it's not 54.
So Alex, I have a question.
Okay.
I didn't even think to pull out my calculator to find these values. I guess
Okay.
I'm just feeling a little overwhelmed at which table I'm supposed to look at. Like, I got the Z-score by just calculating it with the 52 minus 54 over 6 divided by the square root of 50.
Uh-huh.
Like, how? So now I see I did go in my 84 and got that. But like, how would I have gotten that P-score without the calculator? Which table? Where do you get the 0.018?
Well, the p-value. Okay, so the p-value comes directly from the z-value. So, and that's a good question. So I want everybody to remember this z number, negative 2.357. Just remember that, because I'm gonna need it in just a second. So, looking at our z table here, if you're doing this by hand, this is what you would do. You would look in here. I don't have my nice LED light with me, so I'm having to adjust the contrast on this thing constantly to make it work with this silly desk light. So with that negative 2 point whatever, since it's a normal distribution and it's symmetric, this is just giving us the positive values, but the positive values are symmetric to the negative values. So for the sake of looking in the table, we would look up the positive version of that, 2.3 something?
2.35.
2.35. Okay, so 2.35.
2.357. So do I make that 2.36?
Well, sure, we can, it's just right in the middle here, okay? So looking at this is 2.3, that would be 2.35, that would be 2.36, so we're right in the middle, so we can just interpolate this. So halfway in there, halfway in the middle there is going to be like 4908 or something like that, right? Does that make sense?
Yes.
And at that point, we're splitting hairs, so it doesn't really matter. Okay. So, okay, so that is, looking at this diagram, the way this table is set up, that is telling us the area of our data from 0 going one direction. Okay. So if I was to draw this same picture with the information I just got, 0, and here's my 2.36, whatever, right? And then inside of here is 49.08% of the data. Okay? This is a two-tailed test. So that means that the exact same thing is happening over here. Okay? And so you take all of this and you add it up. And we get 0.9816. All of this together is 0.9816. Okay? Now, what's the complement of that? What's the complement of that?
0.0184.
Right.
Okay, thank you.
That's the p-value. Because so that's telling me that with our actual data, we're getting this shaded part here, which is 98.16% of the data, right? So then what's our rejection region? What's left over outside of that is 0.018. That's our p-value.
Okay.
The rejection value that actually exists is 0.018. The rejection value that you are choosing as your threshold is 0.025.
So is the p-value always representing the rejection area?
Yes.
Okay.
So essentially what you're doing is you're calculating your real rejection region. You're calculating your rejection region for your data. And then you're comparing that rejection region that actually exists in your data to the rejection region that you chose when you chose your alpha level.
So since we chose 0.05 because nothing was stipulated, and then you cut that in half because it's a two-tailed test,
Yes.
that's the 0.025.
Yep.
The 0.018 is lower than that, so we reject.
Yes.
Thank you, thank you, thank you.
Yeah. Okay. So whether you do it, I'm just like one of these famously lazy mathematicians, and I hate to calculate things by hand. Sometimes it's easier. Sometimes it's just easier to use this. So I just tend to use this if it's like right next to me.
No, I just feel like as I've gone through the My Stat Lab, like I can see the example, I can see what they're doing. So for that set of questions, like I understand what to do. But then when I have just a general question, I've turned into one of my worst students. That's what's happened. Then I'm like, I don't know. Is it this table? Is it that table? Is it the calculator? So thank you for your patience.
That's a fair point, actually. And maybe, yeah, I mean, the sake of the exercise is definitely valuable. Right. The sake of working it through by hand, maybe I should be more rigorous about that. Working it through by hand really teaches you what's happening. But
well, thank you.
Either way. All righty. So let's go back to our lovely PowerPoint. Okay, so let's move on. So we have confidence intervals here. So some of this Dr. Misteli has typed out. I'm just going to read through it to help us with the narrative. Just stop me if at any point you want me to explain what something means. So because if we were to repeatedly draw a random sample where each sample was a large size from the target population, and afterward each draw we formed an interval, a confidence interval, then we would expect a percentage of those intervals to contain the true population parameter of interest. And I actually have, oh, wait a minute, I'm sharing the wrong PowerPoint. Whoops. Well, actually, I was about to share that one anyway. All right, so. Oh, actually, I wanted to show you guys this table here. That actually follows up directly with the question that I was just asked. So how to translate a confidence level to a critical Z value, Z star. This book doesn't use Z star, it uses Z sub alpha, but it's the same thing as a Z star. It's just, this is from a different book that I teach from sometimes. And how we translate that to a p-value. So for example, a 95% confidence level drills down to a one-sided p of 0.025 and a two-sided p of 0.05. I know that there's a little bit of mystery and vagueness surrounding what is an actual p-value. Like I can compare two numbers, but what are those numbers? Where are they coming from? All it is the rejection region, the tail region, whether it be one-tailed or two-tailed, for the theoretical setup that you want, the confidence level that you want, and then what the data is actually containing. Okay, that's all that is. But let's go back here to this great little picture. So we have some sampling distribution of X bars. We've already talked about that. Hopefully hit that one home really well. And then the mean, the peak value here, the mean value of the sampling distribution is the true value of mu. And then if I was to run lots of these different things, here are 25 samples. All these little arrows represent, each one represents a sample. And that sample ranges from a minimum to a maximum. Notice that the sample contains mu. This is my mu line. It's slicing through all these. My true mu is contained in all of those intervals except for one. And that one interval misses the true value of mu, which is why we are, that's the whole idea of a 95% confidence level or 99% confidence level. We're saying that 95% of the intervals that are possible, running it to an infinite number of times, 95% of those are going to contain mu. And so that's the idea of what a confidence interval, a confidence level is. Okay. So let me make sure I choose the right PowerPoint here now. This one. No, oh gosh, I've got too many windows open. Hang on just a second. I got too many PowerPoints I was looking at earlier. Okay, let me close that one and go to this one here. There we go. Okay, that should be right. Okay, so, okay. All of that happens, that phenomenon occurs because of the central limit theorem. We're saying if we take an infinite number of these samples, the limit, essentially the limit of those means converges on the true mu. But the only way that really works is if we have a large enough number of samples. It does not work well for small sample sizes or if the variance is unknown, because the variance kind of determines the shape and the breadth, how wide or how broad the curve is. And so if it's too broad, then that essentially the central limit theorem is using the fact that bell curve is peak shaped, it's mound shaped, and it's pretty focused going up towards the middle. And so if that peak gets wide enough, then the central limit theorem is saying, well, I'm not really as good now, I'm not really as strong at hitting the right estimate because the data is not helping me out at all. The data is too variable. So if you don't know the variance and you don't know, or if it's a small sample size, the CLT doesn't work. But the samples themselves can still be good point estimators when they are based on their own sampling distributions. And we learned briefly about the chi-square distribution. That's a good example of that. We used that when we were estimating, or when we were forming a confidence interval for variance, which was that the confidence interval that had the two fractions with the chi-square values on the bottom and the sigma square was in the middle, and it was that compound inequality. That's a good example of using variance, basing variance on a chi-square distribution, or something that's not a normal distribution. Chi-square distributions are not normal. And so we can use a calculator, of course. Or excuse me, a calculation to tell us exactly where, how likely it is that our true target population parameter will lie within a certain range. So we do this with one sample, which we have done. An example of this, a new building is being planned and the building specs for plumbing require that the pipes be able to bear a load that is more than 2,400 pounds per foot length. You want to know if the mean breakage strength of these pipes exceeds that 2,400 pounds. Obviously, if it's less than 2,400 pounds, big deal, because that's what the pipes are designed to handle. But if it's more than 2,400, that's what we care about. So this is a great example of a one-tailed test. So your company collects data on the load-bearing pipes for the load-bearing capacity for the pipes. Let's see, are we actually going to do this here? No. Okay. We have our steps to do that. This is exactly the same thing we would have done in the previous example, except now we're just doing a one-tailed test. And we have done these hypothesis tests for different parameters. We've done them for means, and we're going to be doing that. We've done them for variances. I believe we've also done one sample proportions. Pretty sure we have. And we're now going to be learning to do that with comparing two of them, two means, two proportions, two variances. Whoops. Okay, and I talked about this. We did not learn about the non-parametric test yet. There are going to be a couple that we're going to talk about, I believe, next week, whenever Dr. Misterly decides to add that into the schedule. And a non-parametric test, essentially, the nice thing about it is it gets rid of the assumption of normality. Your data set doesn't have to be normal, and you don't have to check for normality, and it still works, which is really cool. There are data tables for all of those in the back of your book. If you're interested to learn more of that, anything that we don't cover in the class, please just let me know, and I'm happy to explain it to you. Okay. So that's what we've done. Now we're going to move into the new stuff where we're comparing two of these parameters. And we'll get through the first half of Chapter 7 tonight. So why would we want to do this? Much more of the interesting statistical questions that you'll run into in your life involve comparing two things, whether it's comparing a before and after scenario, like a testing before and after scenario that's of particular interest to us as in the education field. You may also want to compare two populations to see if there's a significant difference between the two. For example, here, brands of dishwashers, you might want to compare them. Things that are unrelated to each, independent of each other, you can do those. You can test the same student before and after some kind of a learning intervention to see if a desired outcome was achieved by that intervention. And so we've essentially learned all of these things that are already in our statistical tool belt for one sample. And now we're just going to modify them a little bit. We're going to tweak them a little bit, change the way that they're set up so that we can compare two things using what are essentially the same formulas we've already learned. So I want you to realize that the formulas tonight are going to look different, but really they're just modified versions of the things we've already learned. So the structure of the formula is identical as it was before. We've just modified it a little bit to allow us to compare two things rather than just having one input. We're going to have two inputs now. But the structure of the formulas is identical. Okay, so we're going to be doing both confidence intervals and hypothesis testing for this scenario. So you'll be able to figure out point estimates and a confidence interval for estimating a value. And then you're also going to be able to do the hypothesis test that piggybacks off of that to make a statistical decision. Okay, couple of ways that we can do this. We can use, again, remember, we're talking about two populations here. So you can use mu1 minus mu2. That's where you take the mu of the first population minus the mu of the second population. This is a difference between means, or in other words, a difference in averages between two populations. That is going to be for two independent samples. Two independent samples. And I was talking with, I believe, Jennifer about this earlier. This whole idea of a paired sample. Some of you are doing paired samples for your projects or for your thesis, but a mu sub d is a mean of paired differences. Now, a paired difference is different than just subtracting two things. A paired difference is normally, in most of the time, is where you have that you're observing the same observational unit, whether it be a person or a sea turtle or a whatever, a battery, and you're observing that observational unit, that same person, before and after something happens to them. So the samples are not independent. In fact, there's just one sample. but you're measuring the sample twice, and it's the same observational units that are being measured both times. And so you have to take all that into account, because you know, if you were to compare, a great example of that is test scores before and after. A lot of educational settings, we're using paired experiments because we're looking at a single student. You know, we're not looking at a single student, but we're looking at a whole class or a whole school or something. But we're looking at individual students and how each individual student did before and after something was done. That's a classic example of a paired experiment, because the fact that the same student was measured before and after, that's important, because then we're not just randomly comparing random students to other students. You know, if you had a student that scored really, really well the first time, maybe they got a 95 the first time, and then after the intervention they got a 97, like that's not a very significant increase because they already started out really high. But a student that starts at a 60 and goes to a 97, that's a big difference, right? Even though they've ended up on the same number, 96, 97, I don't remember what I said the first time, but they've ended up at the same place, the 96, but they started out somewhere very, very different. And that's why you can't just mix and match those students, because then the progress of each individual student is the significance. I hate to use that word because it kind of has statistical connotations, but the importance, the meaningfulness of each student's progress and comparative progress to each other, all that's lost unless you do a paired experiment. So that's what we're going to use mu sub d for, is if we have essentially one sample, like a class of students, you know, my Math 644, sections 1 and section 2, spring 2019, and I measure you guys before something and after something, that's a paired experiment. We also have a situation which we're going to learn Anova, which is great. Anova does a lot of good stuff for us. Anova just stands for Analysis of Variance. That's just an acronym. And so that's where we're comparing multiple mu's from multiple different scenarios. And that'll work for any number of k different independent samples. Okay, so we're going to learn Anova next week. We're going to learn the other two this week. I believe that's how the schedule is going to work out. Okay, so independent sampling, super important if you're doing this mu1 minus mu2 setup. Independent sampling is a must. Okay, select of course it has to be random. Select a random sample from the first population and then a random sample from the second population. Just as we did before, we're going to look at large samples that use a z statistic and small samples that use a t statistic. Okay, and just like before, we will look at sample statistics to understand why they can be used as unbiased estimators for each population parameter. So here's an example. A dietitian, that's spelled correctly. Okay. A dietitian developed a diet low in fats, carbs, and cholesterol. She created this diet for people with heart issues, but decided to see if it works on reducing the weight of obese people. She collects a sample of 100 obese people from two populations. One that uses the same diet as the people with the heart disease, and the second group that has a similar diet, but it's not as restricted. And so it's like we can think of that just like a regular diet, right? So we have two populations. We have the restricted diet and the not restricted diet, or the heart people diet and the non-restricted diet. Okay. She records the weight loss for all of the people for 3 weeks, and we're supposed to form 100% confidence interval, a 95% confidence interval for that data. Okay, so here's our data. Now, I love this example because it really kind of illustrates why we can't just take a visual guess and jump to the conclusion of something. Because I don't know about you, but looking at these tables like this, you know, you might want to you might want to jump to a conclusion and go, well, I see lots of larger numbers. I see more larger numbers on the top, and in fact, there's a 20 and a 21 on the top group. That's the low-fat diet. So it's got to be bigger, right? Because the differences are bigger. The weight losses are bigger. So that's got to be more effective in that. But statistically, nobody would take you seriously if you were writing up a report for that and said, well, I glanced at the data. I gave it a, like a kind of estimate, like a one-eye thing. And that's what I saw. So that's what my conclusion is, right? There's no mathematical value in doing something like that. So we are going to learn how to appropriately and mathematically, again, backing it up with all that mathematics that we talked about earlier. We're going to back up this process with mathematics and come to an actual mathematical calculation process for calculating this and determining if or in this case, we're looking at a confidence interval. We'll actually calculate the confidence interval, okay? So our old-timey confidence interval for one sample looked like this. Does that ring a bell? You had your point estimate of x bar, then you had plus or minus, and then you had your z value times sigma. And that z times sigma gave you your plus or minus, margin going either direction to cup off your confidence interval. And then smack in the middle of that thing, smack in the middle, was the x bar. Okay. So now we're just doing the exact same thing, but we're modifying that because now we're not interested in just an x bar. We're interested in a difference of x bars. We're interested in the difference in the weight loss diet people and the regular diet people, right? How much of a difference there is in the two. So it's like we're putting them on a scale and weighing them and see which one is heavier. So the way that we modify this is instead of the point estimate being a single value, the point estimate is a difference. We're still using z just like we have before, and then we have to just modify our sigma to be the sigma for that difference of means. But how do we calculate the difference in the standard deviation part? Here it is right here. This new sigma that we're using is essentially just an adjusted sigma for two samples. And this is a trick that we use a lot in mathematics where we square something. We want to find, and we do it a lot in statistics too. We take the sum of squares. So notice here, I've gone from sigma to sigma squared and sigma to sigma squared, and I take the sum of those squares. Notice that radicand is just a sum of squares, right? And then I square root the whole thing to get rid of the squaring that I did. That's a old trick in mathematics. And so that's all we're going to do here to this sigma to get this adjusted sigma of the difference. Okay? So recall that for a large sample, the test statistic S squared is a good estimator of the population's variance. And that again goes back to the central limit theorem. So as we get larger and larger and larger, our S squared approaches sigma squared. And so if we don't really know sigma squared, we can just use S squared, and it's pretty good most of the time, and it's okay. All right, so we can use that for that case. So that changes the formula here to this, which the only difference now in the numerators, under the radicand, is just S instead of sigma, but we didn't know sigma, so no harm, no foul. Okay? We're typically given the sampling standard deviation, not the variance. We're typically given the standard deviation, the S, not S squared. So you're going to need to square it to plug it into the formula. That's just a little, logistical note. Everybody got that? Just note, this is S squared that I'm talking about here. So if you're given S, you do have to square it in the formula. So let's see what we get. If you take this data and calculate all of the descriptive statistics like the mean and the standard deviation and everything else, you're going to get these numbers. The first one gives you a mean of 9.31. The second one gives you a mean of 7.40. We're at 95%. I know that because I'm looking at a z-value of 1.96. That's 95%. And back here it said to use 95%, so that's where we're getting that. And then under the radical, we just have S that we got from the S from just running this descriptive statistic. We got this S the same way. We square them, divide by n, which was 100, which we already knew from the problem. Run it all through the calculator, and we get that. We get 1.91 as our point estimate, and then our margin of error of 1.21. So let's stop and interpret that for a second and try to understand what it's saying, because this is our first day that we've been looking at. Not really the parameter that we're looking at is not, that does not come directly from one set. It comes from two sets. So let's think about what that means. So that is a point estimator. If you just follow down the algebra here, that 1.91 is what is this x1 bar minus x2 bar. Well, what is x1 bar minus x2 bar? Well, this is x1 bar up here is the average of these, and x2 bar is the average of these. So if you're subtracting these numbers minus these numbers and you get a positive number out of it, that means that the top set is larger, right? Because the difference remained positive, okay? So if the difference remains positive, then you know that the top values are larger overall, and that's a weight loss value. So that makes logical sense because it's a low-fat diet designed for weight loss. So we would expect these numbers to be larger. And then earlier when I gave you the little, eyeball method, like that's what it looks like. Now I actually know for sure, and it's not just based on my guessing or my visual inspection anymore. It's actually based on calculating these things, okay? So we would expect this to be a positive value, but of course we're not going to incorporate bias into the experiment. But what we can stop and just do a little mental check right here and go, oh, well, my difference is a positive value. That means that the one set, the x1 bar, which was my weight loss diet, that is a larger number, a larger x bar, okay? A larger x bar than the second x bar. And so that's telling me immediately, that's telling me that my difference leans towards the weight loss diet people being larger, having larger weight loss numbers, okay? So that's just a little visual logical check on what's going on there. So this is like we're doing the one population parameter because we're taking the difference of the two weights, okay? So keep an eye on this. We are creating a third set of data that is the differences of the weights, the differences of each element in the set, okay? So we have one set, we have two sets. When we do the subtraction, we get a third set, and that third set's what we're actually now, what we're analyzing, okay? So this behaves exactly like everything else we've been doing. This is a sampling distribution in and of itself. The differences, the difference set, x1 bar minus x2 bar, has a sampling distribution of its own, has normality of its own, has all the same properties. All those properties from each of the parent sets carries over into this new set of differences, and the whole thing behaves just like anything else that we would expect, which is great because that means that everything we've learned still applies, Okay, so just because we're creating a third set of data out of thin air does not mean that we're losing detail or we're losing usefulness. And preserving those kind of characteristics is really important if all the stuff that we're doing is actually going to have any meaning or not. So luckily, everything behaves exactly the same. The sampling distribution behaves exactly the same as both the parent sets. So everything is still good in the hood. Okay. So using our two diet example, let's find a 95% confidence interval. So take a second on your calculator of choice or by hand if you wish. You, go through and collect and calculate the 95% confidence interval. See if you get the same numbers that I got above. Okay, so I have any volunteers to share? Were you able to get the same numbers that I got above? You should have gotten these numbers.
Approximately. That was awful.
Okay. Anybody else have a problem getting those numbers? Anybody confirm that they were able to?
Yeah, I got the same thing.
Got it. Got it. Okay. Okay, good. Good.
Should it come up like 0.001981 for a p-value?
Well, we're not running a hypothesis test yet.
Okay. Okay.
Yeah, we have no critical value for the mu, so we aren't able to run an hypothesis test. I don't know what it would be testing. So, okay.
Well, I got that when it said mu1 not equal to, or mu not equal to mu naught. So I guess we were testing the two averages against each other.
No, that's not how that works. So,
or wait a minute, no, mu1 not equal to mu2. Excuse me.
Right. Well, that's again a hypothesis test.
Right.
I haven't taught you how to do the hypothesis test for two samples yet.
Okay, so then I just put everything into the wrong thing in the calculator.
Yeah, this is just a confidence interval. That's
okay.
all. That's all that we learned here is just a confidence interval here.
So I did the same thing. I got that same number. So on the calculator, like I've got a TI 84. I put those numbers in, but apparently I chose the sample 2 test. What should I have done differently?
Okay, so
should, like, for the mu1, for the very last thing, it has mu1 and then a colon not equal to mu2 or less than mu2 or greater than mu2.
Right. So I'm pulling it up in mine. Just give me a second. Okay, so here. All right. So Okay, calculator. So this is going to be different if you're on a 84, but the menu item is going to look the same. So here we're doing a confidence interval, so this is going to be under intervals. And you're just doing a 2 sample Z interval right here. So 2 sample because we're comparing the weight loss diet people to the regular diet people. It's a Z interval because there's 100 of them, so it's large enough to be Z. Make sense? And so the options that we have are sigma 1 and sigma 2, x1 bar, n1, x2 bar, n2, and then our C level. So let me look at this and see what we've got. What are our numbers? Okay, so sigma 1 is again going to be S1 because we're large enough that we can use it as an okay estimator. That's 4.67. And by the way, the sigmas and the X bars, those are just direct calculations. I could get those, just so we're clear here. Those are direct calculations from this. If I just put all these numbers in Excel, I could just use, the equals STDEV to give me the S, and equals average to give me the X bar. Those are just direct routine calculations right from here. So there's no magic or trickery there. So looking at our numbers, we've got 4.67 in the first one, 4.04 in the second one. X bar 1 is 9.31. N was 100. N was 100 down here too. X2 bar is 7.40. And then our C level was, I believe, 0.95. And so we just hit enter. Enter. And then here's our 1.91 plus or minus the margin of error, 1.21. So 1.91 plus or minus 1.21 gives us these actual endpoints. Those are the endpoints of the interval, okay? And I got a message here. What's the message? It's a 2 sample Z interval. Right. Oh, I see what you're saying. So if you go, so Rachel, if everybody looks at the chat box, this is a good clarification to make. So Rachel, if you go to tests, a 2 sample Z
I know where I'm
test.
going, but the slide says to go to stat test 2 sample interval, and I think that's where people were getting the wrong thing.
Oh, okay, gotcha. Yeah, no, for interval, that's a typo. I didn't even recognize that. So for intervals, you go to intervals. For tests, this is when you're calculating a critical value and we're going to learn how to do that as well. But that's a Z test just tests for a critical Z value for your data. It doesn't test, and it doesn't give you an interval of some parameter. In this case, the parameter is mu. So we would be in the interval menu. Okay, let me stop this. Oops. What is going on? Start video. There we go. Okay, so we're going to go back to share this. All right, so I already talked about that. Okay, now here's the Z. Here's exactly what Rachel was mentioning with the test statistic. This is the test statistic that is this. What we're about to do is this right here. So if we go back into all right, so that is tests. This is a 2-sample Z-test. Number 3 right here, 2-sample Z-test. That's what I'm about to talk about right now, okay? So, okay. So, we have 2 formats for this, but notice what's the only difference in these? And I honestly don't know why there are parentheses in the top, in the numerator of the first one. They don't do anything because of the associative property, so you don't need them there. But what's the only difference here between the first formula on this screen and the second formula?
The notation for deviation.
Right. And so in the top one, when the population variance is known, we use it. Ta-da! When it's unknown, what do we use in its place?
The variance of the sample or the standard deviation of the sample.
Right. We just swap it out with S. Now, the only thing that is new here, that this is the way that we have tweaked our existing formula to account for the fact that we're doing 2 samples. The only thing we haven't seen before is this D naught. And D naught is the difference in the population means, mu1 and mu2. This difference is our target population parameter of focus. The null hypothesis is that there is no difference between the 2 sample means, i.e. that they are the same mean. Okay? So, oftentimes, D naught is hypothesized to be equal to 0, okay? It's the hypothesized difference between the actual means. So if we're looking at this, the one-tailed test, notice that you can have the difference in the mu's be equal to D naught, or you can have it be less than or greater than D naught for the alternative. For the 2-tailed version, that is what is getting changed into the not equal to for the 2-tailed version. If, and this is all structured exactly like it was for single sample. So here's our test statistic. And that denominator is that adjusted sigma, where we've seen this radical before in both variations, the sigma and the S version. Okay, so if that's the case, then the rejection region is either where the Z critical value is less, the Z value of the data is less than the negative Z critical value, which is Z alpha, or it's greater than the positive version of the Z alpha when you're doing an upper tail test. But that is exactly 100% identical to what we've already done with single sample. If the Z value of the data is higher than the top critical value or lower than the bottom critical value, then you fall into that rejectionable tail, the rejection tail. So that's the same thing here. And the same thing with the rejection region. If the absolute value of Z, because it doesn't matter if it's going plus or minus, they're symmetric, so it doesn't matter which tail you're heading towards. But if the value of your Z for your data is greater than the halved z critical value, z of alpha over 2, again, halving it because we're splitting our rejection region into two different tails, then that is still going to be your rejection region for this. So all of that is to say that you're interpreting the results of this exactly the same as you would have before with a single sample. So let's stop and think. What underlying concept are we developing? The two samples are randomly selected in an independent way within each of their target populations. That the sampling distribution of the mean differences is normal in shape by the CLT if the sample size is large, again, meaning higher than 30. And again, S1 and S2 as variances will be good estimates for their populations if the sample size is large, okay? So you need to make sure all of this is met before you could do that Z statistic. So here's an example. We have a sample size of 90, which gives us a mu of 100 and a sigma squared of 36. The second one gives us, which is a sample size of 100, is selected independently. It's also normal, gives us a mu2 of 90 and a sigma squared of 64. So why can we use the Z statistic here? What parameters are being met?
The sample size is large enough.
Yes, and?
I'm assuming the
Sigma?
Normal
They're
population.
They're both normal and?
we know the deviation.
Yes, and? Experimental design consideration. What's important about that here? What's critical?
That it's random.
Random, and the two samples are what?
They're independent.
Yes, got to have all those things for this to work. Otherwise, it's not the appropriate test to run. So,
I have a quick question.
yes.
Could you have one of them give you sigma and the other one give you S?
Oh, that's a good question. Sure. I mean, yeah, sure. Because if it's large enough, and these are large enough n's, particularly that second one where n is 100, I mean, I would be fine subbing an S for sigma there. Okay. Okay. So set it up in your calculator. I'll give you about 3 minutes to do that. And this time we're doing the 2-samp Z test. And then tell me what you conclude at the 0.05 level.
When we're putting this in our calculator, do we have to divide our P in half, or is that only when we're doing it by hand and looking at the chart?
Let me see what you're talking about here. So 2 sample z-test. Oh wait, I'm not still on this. There. Okay, 2 sample z-test. You mean with your output?
Like when you press enter.
Yeah. So
Okay.
it depends on this. If you've chosen a two-tailed test, then yeah, you would cut it in half.
So the calculator doesn't do that for me. That's what I'm at. Like,
no, because the calculator is reporting the entire p value.
Okay, so then I need to
entire rejection region.
So maybe that's why I'm screwing things up, I think.
Okay.
Thank you.
Yeah, so the calculator is just running the calculation, and I mean, like I said earlier, all the p-value is this whatever's left over outside of your test, right?
Correct.
So the calculator is just reporting, is essentially taking whatever your numbers are, whatever your test statistic is, and subtracting it from 1, and it's giving you that. So it's up to you to interpret that. If you're looking at one of the tails, then yeah, you're going to need to cut it in half.
Thank you.
Sure.
Okay, this is a 2 sample z-test, correct? That's what we're doing on the calculator?
Yes. Uh-huh.
Okay, because I'm getting a really tiny p-value. Have I made a mistake?
Okay. No.
Okay.
Tiny p-values are fine.
Like to a negative 20, in scientific notation, to a negative 23 power.
Yeah, so then tell me what number that basically is.
I got 5.414 times 10 to the negative 23rd.
Yeah, so what number is that? What effective number is that?
0.
Well, yeah, okay.
0.
0, right.
Yeah. So then your p-value is 0.
Yes. Okay.
So do you reject?
Yeah, if p is low, you reject.
Yep. P-value of 0 is pretty good indication.
Can you press enter? Because I think I put in the right numbers, but I didn't get the same.
I haven't plugged in the numbers yet, so let me put this in here. Okay, can everybody see my calculator? Yes. So let's see what we've got here. So we have a sigma 1 of 36, so that's going to be a sigma of 6. Sigma 2, variance is 64, so that's 8.
I see what I did wrong. I wasn't paying attention. I put 36 and 64. Thank you.
Yep.
Same here.
Okay, x bar 1. X bar 1, excuse me, is 100. N1 is 90. X2 bar is 90, and N2 is 100. We're going to assume this is two-tailed because it doesn't tell us otherwise. Oh, wait, no, actually, which the first population mean exceeds the second population mean. So the first one has got to be higher than the second. That's going to be our alternative right there. If you're looking at the screen on the slide, it says set up a hypothesis test at 0.05 in which the first population mean exceeds the second one. And then we calculate and just go boom. And yeah, that is an incredibly small p-value. So without needing to look at anything else on here, I mean, God, a z-value of 9.8, that is so far out in the tail. That's like you've come this far and you've been going out into the little sliver here for like 2 weeks and you're still traveling out that way to get to a z-value of almost 10. your p-value is so small, it's essentially 0. There's no way that that could ever be a true null hypothesis. So we definitely reject the null. So, okay, that's the punchline to that.
Okay, so will you say that in a formal sentence then?
Okay, so observing a p-value of 0, and I would just say p equals 0.000, because it does, right? If you've got 22 zeros in front of this thing, you can truncate at 3 zeros, and you have a perfectly accurate number. So you can say, observing a p-value of 0.000, comma, we conclude that there is sufficient evidence at the 0.05 level that the first population mean is higher than the second.
Thank you.
Great. Okay, so we're going to take a break, and we'll come back to slide 31 in about 15 minutes. So I'll see you at, we'll say 6:49, 6:50-ish, just to make it around 10. So see you at 6:50. the recording. And okay, so now we're going to go on to a another activity. And so this is in a document that is in D2L. And I'm just going to pull it up here, activity 1. So we're going to go to share, activity 1. All right, let me find activity 1. Okay, does everybody see activity 1?
Yep.
Okay, thanks. So a study of differences in cognitive function between normal individuals and patients diagnosed with schizophrenia was published in the American Journal of Psychiatry in April 2010. The total time in minutes a subject spent on the trial-making test, a standard psychological test, was used as a measure of cognitive function. The researchers theorized that the mean time on the trial-making test for schizophrenics will be larger than the corresponding mean for normal subjects. The data for independent random samples of 41 schizophrenics and 49 normal individuals yielded the following results. And there they are. So our task is to identify the parameter of interest, find a 99% confidence interval for that parameter, and then set up a null and alternative hypothesis and test it at the 0.01 level, which is flowing right out of the 99% confidence level. Okay, so you can use your calculators. I'm going to give you, we'll say 5 minutes to do this. And give me a green check mark when you are done. Okay, just a green check mark when you're done. Got a couple people done. You can also check the chat box, see if you agree with John or not. That's okay, Amanda. Um, yeah, we're going to assume it's normal. Once I get the standard deviation is already the square rooted version. It's the variance that is the squared version. Pardon me for yawning. Once we get more people with the buttons on here, I'll throw up this solution. I have so many windows open on my screen right now. What? Oh, that's wrong. What do you think?
I agree, but will you say the sentence for me?
So the sentence would be, observing a p-value of 0, there is sufficient evidence at the 0.01 level to reject the null hypothesis, indicating that it is more likely that the schizophrenics will be larger than the normal subject on the test, or something to that effect.
Well, aren't you supposed to word it in terms of the null hypothesis instead of the alternative?
That's more of a syntax debate.
Okay.
Some people like to word it in terms of the null. Some people like to say it's more likely that this is the case. I teach it both ways, so it,
Okay.
if you were going to word it in terms of the null, you would say observing a p-value of 0, there is sufficient evidence at the 0.01 level to reject the null hypothesis. That is, the mean time between the schizophrenics and the normal people is not equal to each other. So, but I mean, at that point, you're losing the fact that it's a one-tailed test. That's why I would word this in terms of what the alternative is saying, because that's where you get the significance of the one-tailed test out of it.
Alex, could you tell me what numbers you put in on the calculator to get the p-value? I got all the other numbers, but I didn't get a p-value that small.
Well, I can't, but I can just run the problem for you. Let me see here. This is Dr. Mistely's solution, so I'll just run it for us here. Okay. No, wait a minute. Stats. Wait a minute. Let me just stop. Okay. So what are we doing here? We are doing a activity 1. Okay, so we're gonna do a we're gonna do an interval. We're gonna do an interval, a 2-sample Z interval. We're gonna put stats in. Sigma 1 is 45.45, already given in terms of the sigma. Sigma 2, 16.34. Those are very different sigmas. I hope everybody caught on to that. X1 bar 104.23, N1 41, X2 bar 62.24, N2 49, C level 0.99. Okay. So 41.99 plus or minus 19.2468, which is this. The numbers that I got there were 42 plus or minus 19.2. That's that. That's the same thing. And then is this part okay? Is part B okay?
Oh, yeah, I got part B. I got the same Z
okay.
score. I got a different P score, and I don't know why.
Okay, so let's then do a test. 2-samp Z test. Okay, and then this should have carried over. And the question says, they theorized that the schizophrenics will be larger. Schizophrenics was the one group. So this is our alternative there. 1 greater than 2. Okay. Z value 5.619. P value of.
Oh, no, my fault. I didn't see that it had the -9 exponent.
Oh, well, I'll tell you, even without the p-value being listed, a z-value of 5, anything over 3 is going to give you a p-value of 0.
Yeah, because I wrote down.
Yeah,
I wrote down 9.6, and I didn't see that it's to the -9th.
Oh God, no. Well, also, I mean, okay, so yeah, anything greater than a z-value of 3, automatically you're so far in the tail. If z is over 3. Your p-value is 0. I can even tell you without calculating it. Okay. So 5.6, definitely reject the null.
All right, thank you.
Okay.
Alex, can I ask a couple clarifying questions?
Yes, of course.
Okay, my first one is, I had set up my hypothesis for the null hypothesis. I had written it as the mean, the like mu for the schizophrenia minus mu for normal equals 0. Is that okay to do? Because that's how I'm used to doing it.
Well,
like-
sure, because that's equivalent to saying mu1 equals u2.
Okay, I didn't know if maybe there was like certain situations where it's not usual to write it that way. Like is it considered like usual to write it that way, or does it usually get written the way you wrote it? It doesn't matter.
I think it depends on the scenario.
Right? Like, are there certain scenarios? Because I just want to make sure I'm doing like what seems like the right fit. Like I usually write it as that the difference is 0, so I subtract.
Right. Yeah. I mean, they're equivalent statements.
Okay.
I think a lot of times it just depends on the book, and it depends on who you're talking to.
Okay.
My
other question is, when you put this in the calculator, you get a pretty substantially far. I mean, I guess I wouldn't call it substantial, but it's definitely not the same number when you put it in the calculator versus when you actually use the formula. When we're doing my stat lab, should we be using it according to the calculator, or when you do it with the formula by hand?
Well, tell me what is your hand calculated number?
So when I did it in the calculator, I had what you had, and when I did it by hand, I had 22.747 and 61.23 for the confidence interval. And
Wait, say that again?
Yeah, so when I did my confidence interval, I had I had 22.747 and 61.23. So they're close. And I did the work all right. Like when I did it in the calculator, I got 21.959 and 62.021. So they're close, but they're not the same number, and I'm scared about my stat lab and rounding issues. So are they going to want us to be putting it in calculator form?
Jen, when I did it in the calculator, I got 22.726 and 61.254. Maybe you typed in a decimal wrong.
I see what you're saying. You're saying you're giving me the endpoints.
Yeah.
You're giving me the endpoints. All right,
yeah.
Let's go back to this. So, so you're saying that was 22 point what now?
I had 22.747.
Oh, so your hundredths is off.
But that was when I did it by hand. When I did it in the calculator, I had gotten 21.959. So I don't know.
You have a typo somewhere then, Jen.
Yeah, okay, this is what the calculator gives us, 22.7.
Okay, so that was when I did it by hand, I got it, but then I must have, when I put it in the calculator, maybe I hit a number.
Yeah, you may missed a keystroke or something.
Okay.
Off by hundredths is.
Yeah, no, I was off by more than that, and that's why I was concerned.
Well, yeah, that just means there's an error somewhere.
Okay, because I got my Z-score for part C when we did the test. I got 5.62 for my Z, which was essentially the same thing you got when you put it in the calculator. So that one wasn't so far off. My p-value was still 0.000.
Well, that means 5.619 is 5.62.
Right. Yeah. So that's why I was saying it wasn't crazy off or anything like that. And what would you say for the wording in your conclusion for part C?
I would say observing a p-value of, or if you want to be really thorough, say a critical z-value is calculated to be 5.6, which corresponds to a p-value of 0. Observing a p-value of 0.0 means that at the 0.01 level there is sufficient evidence to reject the null. Or
okay, do we need to know how to say it in terms of the context of the problem at all? Like, should we be able to?
Yeah. Mm-hmm.
Okay.
Yeah. So instead of just saying reject the null, then you
like instead of just like reject the null, we have convincing evidence to support the alternative, like in terms of the context of the problem? How
Right.
would you say it?
So that's where I was saying that it's more fluid in my experience. It's more fluid to frame your conclusion in terms of the alternative and say that the alternative is more likely. Because then it really paints it paints the context thoroughly.
Okay, because I wrote that there's convincing evidence to suggest that the true difference in mean time of schizophrenic and normal individuals is more than 0, meaning that the mean time for schizophrenics is more than the mean time for normal individuals.
That's equivalent to what I just said, so that's perfectly fine.
Okay. All right. Thanks.
Got it? Okay, good. So let's go back to this. All right. All right. I'm about to throw a wrench in everybody's happy party right now. The wrench is small samples. What do we do? Well, there's a whole bunch of stuff we have to do. And as it turns out, it's not as clean or happy as we would like it to be, but we have to do it anyway, so here it is. So if the samples are small, all of our CLT stuff falls apart, which is a big deal. I've got chat messages. Let me check this out. T-test. Of course you do T-test, but you have to be careful. Oh, shoot. You have to be careful with the way that you do the T-tests because of the issue of variance. So comparing two populations or two samples, the variance plays a really big part in that. And if you have small samples, then the likelihood that your variances are not going to be the same goes up quite dramatically. So we have to be careful with this. So again, we're going to use a t-statistic. Both sampled populations must be approximately normal. Again, they must be random samples. They must be selected independently from each other, all that good stuff. So what is new here is this idea of a pooled variance. So it's essentially taking a weighted average of the two variances. And we're going to go through an example of that. But a pooled variance, essentially, if you have two small samples, the smaller the sample, the bigger the chance of a variance inequality, difference in variances happening. So if you have a small samples, let's say one of them gives you a variance of here, one of them gives you a variance of here. If you essentially take a weighted average of those, it kind of is a way of retrofitting an equalizer to it, and that's all we're doing here. And we call it pooling the variances. Okay, if the population variances are equal, then we pool them. If they're equal, excuse me. If they're unequal, then they're unpooled. And we're going to talk about what that is. Okay, so if they're equal, then they're pooled, which is a weighted average. If they're unequal, then they're unpooled. We're going to look at each of those. But the big thing is here is that we're combining two variances. We have two variances to think about. And so instead of our degrees of freedom just being -1, it's now -2 because you're subtracting 1 from the first one, subtracting 1 from the second one. So your new degrees of freedom is actually -2. But that's going to make more sense once we look at the formula. You go about checking normality the same way as before. And then if you've either designed the experiment or you've been given a problem. If you've designed the experiment, I hope you've designed it so that it's random and independent and normal and all that stuff. Random and independent, excuse me. You check for normality using the same tools we've already learned about, QQ plots, etc. If you're given a problem, it has to tell you that it's been random and independent and all that stuff. So, okay. So here we go. Here's some different stuff. All right, this is a small independent sample confidence interval for mu using the t-test. Okay, so we have the difference in the x bars. That's our point estimator. This is a confidence interval, so it's going to be our point estimator plus or minus the margin of error. And our margin of error has the same kind of format as before. T, critical value of t, and then under the radical, and I don't like the way that they've done this. I think that they should have added another step in there to show you the other way of writing this, but look at what's in the radicand here. The radicand is just, all it's saying is that you have the s squared over n1 and n2. They've just factored this out right here because they want you to start looking at this pooled variance type of element right here with the 1 over n1 plus 1 over n2. I'm going to show you more about this right here, so just hang tight with me for just a second. So this s squared, this variance here, this is a new one. We're calling it S sub p. S sub p is what's happening when they're small samples, okay? And it's this large calculation thing right here. So it's because they've written it out here with it factored out in the radicand. They factored it out in the radicand so that it's obvious to you that you're only calculating this large fraction right here, this large s sub p, only once, rather than having to do it twice and realizing it's just the same number in both numerators. So that's why they've written it like this, but I think there should really be an equal sign right here, and they should type out the same thing again and then show it in the numerators of both, because that then follows the same format we've been seeing with this, isn't it? Notice that's the same radical that we had right here. Okay, does everybody see that? I want a thumbs up if you see that it's the same radical we saw before, but now they've just written it with it factored out because it's this big annoying thing. Give me a thumbs up or a green check or a hand or something if you see that it's the same radical. Oops. All these buttons are so small in this control panel. Okay, are we getting, yep. Okay, Rachel, are you giving me a thumbs down because you don't see it or because that was the button you clicked? Okay, now thumbs up. Okay, good. Everybody good? Candace is clapping for me. That's good, a little good encouragement. Thank you, I needed that. All right, so good. So I'm trying to impress upon you that we're seeing lots of formulas, but I want you to realize that the structure of all these things is the same. We're just making small little tweaks here and there for these special situations. And so literally, I mean, I don't have any of these things memorized in life. When I'm given a scenario, I look at the scenario, I think about what's happening, what are the characteristics of the scenario, what are the properties of the scenario, and then I go, okay, so then what test do I pick out? What formula do I pick out that best matches all of those things? And then I look it up in a book. I don't memorize these things. I know that they all have the same structure. So, I mean, I know what I'm doing. I don't waste the mental energy to try to memorize all of these formulas because they're, the little details are minute. They're important, but they're minute. And so I like to have the idea well constructed in my head, but as far as the details, I mean, you know, look it up on a formula sheet or in a book if you need it. So here, the N1 plus N2 minus 2 degrees of freedom, because again, we're pooling the variances and we're pooling the sample sizes, okay? Note that when, this is a good note, so look at this big annoying fraction right here just to find our variance. Okay. Note that when n1 equals n2, it just reverts back to the same thing we had before. So it's just an adjusted one. And if you look closely, all this is doing is it's taking a weighted average. That's all that formula is a weighted average. Okay. So, all right. So what do we do? What are we to do when the variances are not equal? Well, we ask ourselves if we have equal sample sizes or not. If we have equal sample sizes, then we do what's at the top of this box. If we have unequal sample sizes, we change it just a little bit to account for the fact that we do not have the same n everywhere. So I want you to just take a moment. Everybody's going to take a moment. I'm going to give you 3 minutes here, and I want you to just stare at the top formulas and the bottom formulas, and I want you to realize that they are identical to each other if n1 equals n2. The top one, if you plug in n1 equals n2 to the bottom one, you're going to get the top one out of it. So I just want everybody to convince themselves that I'm not saying these are different formulas. I'm saying they're the same formula, but if one is, if they're equal, then you get the simplified version at the top. If they're unequal, you get the slightly more complex version at the bottom. Okay, so 2 minutes, and I'll move on. So essentially all you're doing here is it's just a fraction, you know, with the common denominators, and then you're factoring out, or I guess not factoring, yeah, factoring out, but combining the common denominators with the addition. Okay, so if the sample sizes are equal, you simply just add them together, subtract 2 to get your degrees of freedom, which we already said. That's listed up here in the top scenario. In the bottom scenario, if they're unequal, what do? Well, of course, there's a really big annoying fraction that you have to calculate that gives you this simulated degrees of freedom V. And note that V is not usually an integer because you've got all this squaring and dividing and everything down here. So in very few cases is your V going to turn out to be an integer. And so you just, to be conservative, you just round down to the nearest integer and then take that and go to the t-table. Okay. All right. So example 4. 2 approximately normal populations are believed to have equal variances. A random sample size of 9 is selected from the first. It has a sample mean of 124 and a variance of 10. A random sample from a second population is size 16, random, independent, mean 120, variance 14. So give me a 95% confidence interval and a hypothesis test at the 0.05 level. Go. Okay, we got some intervals coming in.
I always get confused when I've got to make a decision on if it, on my hypothesis test, if
Yes.
it's greater than, less than, or not equal.
So whether it's a two-tailed or a one-tailed.
Yeah.
You're just going to read that in the problem.
That's
Let me see what the problem says here.
I couldn't figure that out from the problem either.
Okay, so if it doesn't say, then you assume that it's two-tailed. Yeah, just like if it doesn't say what the significance level is, you assume 0.05. If it doesn't say which direction the tail is in the test, then you assume it's two-tailed, and you just get both of them. 2 for the price of 1. Okay, we got Mary is confirming Karen's result. Okay, Shannon is saying fail to reject. Let's get some people confirming or denying that.
Is it pooled or not pooled?
Oh, good question. What do we think?
It's pooled because the variances are assumed to be the same.
Okay, thank you. I didn't want to hit the button until I had an answer to that.
Right.
Is that right?
Yep. That's right. Believed to have equal variances, so you can pool it. Okay, I'm with Shannon. Yep. Everybody's confirming. I had said unpooled. Mary said unpooled. Yeah, we'll pool this because they're the same variance. Take the square. So all the square root issue is the fact that sometimes you're given s, sometimes you're given s squared, and you need the opposite. If you're given s squared and you need s, that's when you take the square root. But if you're already given the square root, if you're already given just s, then square rooting s gives you something. I don't even know what that is. It's not useful.
So which one was I given in this problem?
We are given variance, right? Variance. We're given variances, so that's s squared.
Okay, so I do need to take the square root.
Yes, variance is the squared version.
Why is it pooled if the variances are different?
The population, let's look back here. The population, if we assume the population variances are equal, then the sample variance estimator is pooled. So we're given that the population variances are equal right here in the first sentence. The sample variances are unequal, 9 and 10, but the population variances are believed to be equal. So we can pool the sample variances. That's the importance of that. And I have solutions to all of these example problems that are in the PowerPoint that I'll be putting up on D2L after class tonight. Yeah, I'm getting what Amanda said, a p-value of 0.01. So we reject. Okay, let's run it through the calculator here, just to clear up the confusion. Sure I need to. There we go. All right. Yeah, I mean the hundredths place is just, or the thousandths place, Jennifer, is going to be, splitting hairs on this. All right, let me look at what I'm doing. All right, so we're doing a two sample. This is a confidence interval, so this is a 7. I'm in part A here. So two sample t interval here. That okay? X1 bar 124. S of X1 is root of 10. N1 is 9. X2 bar 120. S of X2 is root of 14. N2 is 16. Confidence level 0.95. Whoops. Shoot. There we go. All right, so wait, I'm looking at the wrong screen here. Everybody see this? There's my interval, otherwise known as 4 plus or minus 2.94 or 2.95.
That's the interval I got when I did it unpooled, and then I did it pooled and got a different one.
Okay, let me look at the Oh, yep, you're right. This needs to be pooled. So the pooled is 12.61. So this is going to be, thank you for catching that, whoever that was, 2 sample T interval. This is going to be the square root of 12.61. Okay. This should change it to a 3. My margin of error should be 3 something. Yeah, 3.12. Okay, Mary, you're getting, wait, where did you go here? Okay, let me make sure I'm doing this right. 2 sample Z interval. Oops. Yeah, 2 sample Z interval. No, T interval. Oh, that's what I was doing wrong. Okay. So, what am I screwing up here? X1 bar. I'm looking at the PowerPoint slide, even though you're seeing this. So, X1.
So why do you have to square root of 12.61? It is the square root of 10?
Because we're pooling the variances.
Okay.
So that's
right,
that's that big annoying fraction I showed you.
Okay, got it.
But I assumed that my calculator took care of that. I'm using an 84 because it asked the question pooled or unpooled.
Oh,
Me
okay.
too. Like that's my same thing.
Pooled is yes. Oh, okay, here's we go. I was not scrolling down far enough. Okay. So it will take care of that for us. Yeah.
So you're just putting in your normal standard deviation and then you click pooled or unpooled, or leave it if it's on.
This is what you should be getting right here. You have to put in the pool. You have to calculate the pooled version, or
yes, I match.
Yeah, at 4 plus or minus 3.06. Let me try this a different way. Let me just try it with, just to clear up any confusion here. Let's try that. Oh, I did it again. Wait, escape.
So as long as you have an option for pooling or not pooling, then you put in the 2 different standard deviations.
Well, I did it by actually putting in my pooled number here, which was 12.61. Now I'm going to go back and try it with 10 and with 14. I think the calculator should correct for that, but let's see if we get the same. We should get the same numbers out of it this way.
And you're going to click pooled for that.
Yes. Yeah, we get the same numbers, 3.061. So it looks like it's different at the 10,000ths place, but you know, who cares? So 4 plus or minus 3.06. So we're getting the same. I hope everybody is seeing what I'm doing here. These numbers, 4 plus or minus 3.06, those numbers will come out whether we type in the actual S here and the actual S2 here, 10 and 14, and click pooled, or if we actually figure out what the pooled number is, in this case it's 12.61, not 112, oh gosh, 12.61, and then just duplicate that here. If we actually put those in and then still go ahead and say pooled, we're going to get the same numbers out, 4 plus or minus 3.061. Okay, but it's different at the 10,000 at the 10,000th place. But
so
okay.
Alex, we're supposed to be using the pooled when the variance is assumed to be the same.
The population, yes, the population variance.
The population. Okay, so the sample variance that you gave us, those aren't going to be necessarily the same, but this is a situation where we assume the population variance will be the same.
Yes, if the population variance is the same, then you can pool the sample variances.
And will it say that in the problem? It'll say that in, the
Yes.
population. Okay, so it'll just let us know.
Yes.
It'll say that. Okay, thank you.
Yes.
One last calculator question.
Yes.
On the 84, it doesn't give us the ME. Is that something important, or are we just more concerned about the interval?
Well, these are the same thing. If I take 4 minus 3.06, I get 0.939.
Correct. I understand that, but I just wasn't sure. Like the 84 doesn't have any. It doesn't have. I can't read the first one. What's it? Z something. That's 1 minus 2 or something.
X1 bar minus
X2 the 4 bar. It doesn't have the 4 for the 4 or so the 4 I see I can figure out the 4. I gotcha.
Well, all you do is you take the difference between the top and the bottom bounds of the interval, divide it by 2. That gives you 4.
I just wasn't sure if we needed if we would ever be asked for the ME.
Well, sure. Yeah, I mean, sometimes you'll report it as the interval itself. Sometimes you'll report it as 4 plus or minus 3.06. Both are useful because the interval gives you the bounds of the estimation. The 4 plus or minus 3.06 is useful because it gives you the point estimator right in the middle, which is 4.
Thank you.
So both are useful in different ways. But if you only have one, you can figure out the other by just doing a little bit of routine arithmetic. Okay. Checking assumptions. I'm going to put this on D2L, just be sure you read it. Normality assumptions, same as usual. You can look at a histogram or QQ plot. Variances, we're going to learn something new, not today, but we're going to learn in a week or so. Going to learn something called Levine's test that we can check for equal variances. So you're familiar with looking at these. This is just a nice little chart about what QQ plots tell us. And I wanted to dispel a little misnomer I heard with some students. If it's linear like this, that means that the data set is normally distributed. It doesn't mean anything about a linear relationship between anything. A QQ plot takes the density function of the distribution and just does a linear regression on it. And that's all it does. And the more linear it can be regressed, the more normal it was to begin with. That's all that means. But these other shapes tell you different things. Okay, a paired difference experiment means that the two sets of data, so we're in this two set of data realm, it means that the two sets of data are connected in some way, or the random selection for each population was not done independently of each other. So there was a question earlier by a student here about whether something was paired or not. And I had originally said that it was not paired because you were talking about two different people. They were twins. But the more that I thought about it, and this student asked me again about it, and the more that I thought about it, I thought, well, it might be paired because the twins are not selected independently of each other. They're selected they're selected because they are each other's twins. And so in that sense, there is some pairing going on. But the main thing to think about here is that usually with paired experiments, you're talking about observing the same person before and after something has happened. Here in education, a pre-test and post-test, that's classic example, or some intervention or instructional technique, and you evaluate each individual student before and after, and then you look at the changes of each individual student's measurement before and after. Okay. The bottom line is this means the two populations are dependent, and so everything we've done up until this point no longer applies. Okay. So this is this parameter mu sub d. That's going to be this paired difference. Mu sub d, the subscript d, referencing the difference of the mu's. Instead of having them discrete as mu1 and mu2, now we are obscuring the discreteness of the first and the second data set because they are paired. So we're not actually considering them as independent data sets. We are merging them into a large data set of differences, and that is what we're going to be looking at now with this parameter of interest, mu sub d. But I want you to think about, why is this different than the parameter we looked at before when we looked at here, when we looked at mu1 minus mu2, what we've just been doing previously in class tonight. Those were independent. Now, all of a sudden, we're not independent anymore. That's why we have this new contraption called mu d, okay, because those are dependent now. So, okay, still has to be random. That's the big thing. It still has to be random. Sample size needs to be large for central limit theorem to work. Okay, so again, 30 is our magical / textbook / arbitrary / generally accepted cutoff, as I've talked about before. Degrees of freedom is the number of those differences minus 1 when using t-test. We're subtracting minus 1 now, not minus 2, because we are considering all of the data as one data set. We're formulating a new data set of differences rather than looking at two data sets that are independent of each other. We're looking at one data set. And so that's why the degrees of freedom is just minus 1. Okay, so let's look at how our formulas have changed now. Confidence interval for Z. Okay, looks pretty familiar. Pretty familiar. Only difference is we're now looking at the sigma of the D's and the n sub D, the number of differences. So let's say, and why is this n sub D important? Well, let's go back to the pre-test and post-test scenario. So let's say that we're collecting pre-test and post-test data, and on the first day of class, Mary was, or not Mary, sorry, we have a Mary in the class, I don't know, Josephine was sick. So Josephine did not get the pretest, and then Josephine was there for the post-test. So we have post-test data for Josephine, but not pre-test data for Josephine. Can we include Josephine as one of our n sub D? No. Chat box. No, correct. So even if the class has 35 people in it, the roster has 35 people on it, and 34 were there the first day and 35 were there the second day, then my n sub D is only 34, because Josephine is not a valid observational unit anymore. Okay. Of course, don't tell her that; it might hurt her feelings. So if we're doing with S is a good estimator for sigma here, as it has been, because we're in Z territory. We're large enough that S is approaching sigma. So if we're in Z territory, we can confidently replace sigma with S, and it'll behave just fine. In T territory, we don't really have that, but in T territory, we're not really looking at sigma anyway because we don't know what sigma is, so it's not an issue. So it's the same structure for that. Notice this X bar sub D, that is of just the sample mean of the D's, okay? Similar situation is happening with the hypothesis test here. And I'm aware of the time, I'm keeping an eye on the time, so we may have to cut a couple of activities short tonight, but that's great. I'm glad we were able to get some of the calculator stuff cleared up. So I just realized you've been staring at my calculator screen for a long time. So hypothesis test now, okay, paired differences. We're now looking at mu sub d, which is mu1 minus mu2. It is still the differences. We're subtracting the two to get a difference, but it's different, no pun intended. It is, it's not the same thing as the original mu1 minus mu2 parameter that we were looking at the beginning of class tonight, because again, these samples are dependent on each other. So the arithmetic is the same, right? We're still just doing a bunch of subtraction to figure out what we're comparing, but the rationale behind it is very different because one was independent, one is dependent. So that's why we call them different things. I also like to think about this mu sub d, the d meaning dependent, just to remind me that, oh yeah, if I'm using mu sub d, it's because they're dependent in some way. So just a little fun fact. Notice that the one-tailed test is set up just like you would think it would be. The two-tailed test is set up just like you would think it would be. The z-statistic test is set up exactly how you would think it would be, because what is that d0? Or the d, excuse me, d naught. D naught is the theorized difference in the samples, right? So if we're looking at this shift from an X bar to a theoretical value, right? Normally it's mu, isn't it? If we're thinking about the mu as being a D naught instead of a mu, because we're not looking at a mu anymore. We're looking at an X bar of the D's. And so if that is our sampling value, right? We've got two sets. We've taken their differences, and now we've got this new set of just the D's here, okay? So we take that average. I could just put, those are just numbers. I could put them in Excel and do equals average, and, you know, and then I'm good. So think about the magnitude of those values, all right? So if, let's say my first X bar was like 80, my second one was like 70. The difference there is 10. So I'm no longer dealing with those large 80 or 70 value numbers, right? I'm dealing with much smaller numbers because I've taken differences. So my mu, my regular old mu, is no longer really going to be applicable. I've got to replace it with D naught, because that's my theoretical, idealized, pie in the sky, you know, value of the differences. Not the mu, but the differences, right? And so the rest of the setup here is identical, even with that t statistic. Even with that t statistic, we're just substituting here. Notice for z, we can replace sigma for s if we need to. The rejection regions are identical. Here, the rejection region for the two-tailed test, the absolute value, is greater than the halved critical value. Here, it's just lower than the negative version or greater than the positive version if we're doing an upper-tailed test. The t-statistic is the same setup, okay? The rejection regions are the same setup. And again, we're basing all the t stuff, we're basing all the t stuff on n minus 1 degrees of freedom, okay? And so the next thing on the PowerPoint here is example 5, and that's where we're going to pick up next time because it's 8 o'clock. And so I will stop here. If you have any questions for me, just hang around and ask me. And I thank you all so much. Have a good night.
I have a question. What is
Sure.
our assignment for this week?
Oh, good question. Let me share the syllabus. Today is 3/27. So you have quiz 3, which will open up on the 29th. So it'll open up on Friday, and you have to do it this weekend. And then you just have research project part 2, which is due April 2nd, which I think is next Tuesday.
Alex,
Yes.
is there any way you could ask her to extend our quiz till Monday? It's the beginning of our spring break.
Yes, I will definitely ask her.
Or something, just because we're going out of town.
Yes, so quiz 3.
If there's some way she could give us an extension, would be appreciated.
Extension to, I will.
At least until like maybe the Monday before, like when we come back or something like that, because.
Okay, I will certainly ask her.
And I don't know if all the people in this class, but Chesterfield County, and a lot of us are Chesterfield, our spring break starts Friday.
Right, I get it. I have the software clearance to make those changes, but I do not have the authority to make those changes. So
I understand.
I'll ask her for that.
Thank you.
Yeah, sure.
Alex, did you do activity 3? Is that a paired one? Or are we going to do that next time?
We'll do that next time. Yeah, that's 2 slides away.
Okay. Are you able to put those in the calculator, or you can't?
Activity 3?
Yeah, just anything with like the paired mean. Are you able to put those in?
Oh, sure.
I couldn't find anywhere to put that because it was just the 2 sample t interval. But
oh, okay, I see what you're saying. So really what I would do for that is I just use Excel and just have a column and then another column, and then just do this one minus this one, and then I just populate the 3rd column, and then those are my.
Oh, because you don't need 2 sets of data. You just need the one where it's the difference.
Right, and then I use Excel again to give me a new mean and variance, and then I go right back to the calculator.
That makes sense, because then you use the two interval, but with the paired difference as your set of data.
Right, with the D's, it's essentially just a 1 sample situation.
Oh, so you'll go to right. So you'll go to 1 sample t interval, and you'll use the difference.
Because you're not looking at the end. You're not looking at the discretized data anymore. You're looking at this new.
Just the difference.
1 set of data that's just the D's. Yeah. Mm-hmm.
Okay. Thank you. Have a nice week.
Yeah. Thank you so much, Alex. This was great.
Okay. Great. Thank you. You're welcome.
Good night.
All right. Good night, everybody.
Do you know when our part 2 project feedback's going to be posted?
I don't. I will ask her about that as well. Part 2 of which of the analysis project?
For the analysis project, because I know I asked earlier, like if she was going to push back part 3 if she's inserting.
Mm-hmm.
But we haven't got our part 2 feedback yet.
I'll ask her about that.
Thank you.
As well. Okay.